Hello everyone, Godongwane, the Native God here. Right, on this video we'll be looking at how we would approach a problem on flywheels. Right, now problems on flywheels require that we have a strong background in angular motion, right? Because most of the problems that you are going to come across as far as flywheels, you can simply look at face value and you are able to solve them, right? By that I mean most of the problems you'll be able to look at, and then based on your knowledge of flywheels, you'd be able to look at what you have um, in conjunction with what they are looking for, right? And just use angular motion in solving the problems, right? Now, for this problem we're looking at in particular, right, we've been given a diagram of the flywheel, right? The diagram of the flywheel is from two perspectives. We have the front view, which is this one, and then we have a sectional view, right? Now, the sectional view, the cutting plane of the sectional view would be this one, the one that I've labeled as XX here, right? Now, both perspectives are important, right? And you're going to understand why when we go through the problem, right? Now, as far as the parts of the flywheel, right, this part here is the rim, or we denote this part as the rim. This here, right, can either be called the arms, or the spoke, right? And then here, right, we have, this is where the shaft, this is where we get the shaft, right? And then this here, right, I have labeled as the boss, but sometimes it is also referred to as the hub, right? Sometimes they would call this the hub, right? But for now, we are going to refer to it as the boss, right? And then, like I said here, this can also be called the arm, right? But we will predominantly refer to this as the spoke, and will predominantly refer to this as the boss, right? Right. Now the problem reads as follows. The flywheel has 6 elliptical shaped spokes, right? Before we go any further, the spokes, right? Spokes come in different profiles, right? The profiles of a spoke can be elliptical, they can be rectangular, it can be an I section, right? It can be an H profile, right? So based on the profile of the spoke, right? The profile of the spoke suggests to us how we should go about calculating its area, right? So the fact that this is elliptical, right, gives us an indication of how we should calculate the area of the spoke, right? And is keyed to a shaft with a diameter of 100 millimeters and a length of 1 meter. Assume the density of the flywheel material is 7,200 kilograms per cubic meters, right? Now, the way we go about such problems, right, we have to calculate the mass, right? We have to calculate the mass of each part. We need to calculate the radius of gyration of each part, right? Because normally for such problems, they want us to calculate the total mass moment of inertia. Like for instance, if you look at 3.1 here, right? If you look at 3.1, they said calculate the moment of inertia of the flywheel and shaft assembly around the axis of rotation. Axis of rotation being this one. Being this one, right? Then the second question is calculate the radius of gyration of the whole system, right? Now, like I said, for such questions, we predominantly need to calculate the mass of each part, the radius of gyration of each part, as well as the mass moment of inertia of each part, right? So first thing we're going to do is calculate the mass, the radius of gyration, as well as the mass moment of inertia of each part, right? So we will begin with the boss. So we'll start with this part, the boss, right? All right, so we'll begin with the boss. First, we're going to calculate the mass of the boss. Right, so now we've been given the density of the material, right? Hence, to calculate the mass, it will be the density of the material. So rho times the area times the length, right? Now rho remains rho. Now the area, right? The area of the boss, right? So the area of this boss, right? This will be pi r squared essentially, right? But remember now the boss is hollow, right? So we would have to say the radius, right, of the boss essentially. So the radius from here to there, right, which is this 90 millimeters. So that radius squared minus the radius of the shaft, which is this radius here. Now we've been given the diameter of the shaft, right? So half that would be the radius of the shaft, right? So the area is pi into the radius of the boss squared minus the radius of the shaft. So SH is for shaft squared, right, times the length, right? The length of the, or is the length of the boss, right? Now the length of the boss we get to see, right, from this perspective, right? So the radius, the length of the boss would be this one here, the 150 millimeters, right? The length of the boss we see, or we get to see only from this perspective, right? So only from the sectional view or the side view, right? So this we would see from the side view, the length of the boss, right? So now we substitute. So this here is 7,200, right, times pi into the radius of the boss, right? As I've mentioned, the radius of the boss is from here to there, which is this one here, right? So from here to there is 90 millimeters, so that's the radius. So the radius here is 0.09 squared, right, minus the radius of the shaft. The shaft, that's the diameter of the shaft, so we are looking for that radius, which is going to be half the diameter. Half of 100 is 50 millimeters in meters is 0.05 squared, right, times the length, which we've established is equal to that 150 millimeters, which is 0.15. Right, now if you punch this in your calculators, we are going to get 19 kilograms, right? So we've calculated the mass, so now we calculate the radius of gyration, right? Radius of gyration would be k squared, right? Radius of gyration of the boss, so B stands for the boss, right? Now the easiest way of looking at this is to calculate the radius of gyration of the boss, right? If you look at the area, right, it's simply going to be half. Now if you look at the area is the radius of the boss squared minus the radius of the shaft squared, right? For the radius of gyration, right, so we're essentially going to use the same thing, right, but we're going to add this now, right? So this will be radius of the boss squared plus the radius of the shaft squared, right? That is how you calculate the radius of gyration of the boss. So now you substituting this 0.09 squared plus the 0.05 squared, right? Now if you punch that in your calculators, we are going to get 5.3 times 10 to a negative 3 meters squared, right? So we've calculated the mass, we've calculated the radius of gyration. Now we calculate the moment of inertia, right? We calculate the moment of inertia, so we calculate I of the boss. We know the radius of gyration is, not radius of gyration, the moment of inertia is mk squared, right? We have both M and K, right? So this would be equal to, we got 19 here, and then here we got 5,3 times 10 to a negative 3, right? Now remember that our radius of gyration is already squared, right? So we already have K squared. When you calculated this, right, is equal to K squared and not just K, right? So meaning we substitute this exactly as it is, right? Now if you punch this in calculators, we are going to get 0,101 kilogram meter squared, right? Now we are done with the boss, right? So now we are going to move on to the spoke or the arm, right? Right. So we are going to do the very same thing for the spoke, right? Calculate its mass, the mass of the spoke. So S stands for spoke, right? So even with this one, this is equal to rho times the area of the spoke times the length, right? Now we get a number of spokes, right? As indicated in the statement, they said the flywheel has six elliptically shaped spokes. So we have six number of spokes, and the number of spokes we use in calculating the mass. So here you would then say times number of spokes, right? So this essentially will be equal to, now how do you go about calculating the area of an elliptically shaped spoke, or a spoke with the elliptical profile, right? So this would be rho times, now the area, right? The area, how we calculate the area of a spoke is, right, now an ellipse is shaped like this one, right? So this distance, right, from here to there, we're going to name it as A, and that distance we're going to name it as B, right? So to get the area, right, to get the area of an ellipse, it is actually, it's pi over 4, right? Pi over 4 into A times B, right? And then times the length, right? The length of the spokes times the number of spokes, right? So what essentially this means is that to get the area in an ellipse, right, it's actually, so if you look at what is this, if you look at what we've been given here, right, on our spoke, what's this thing, right there. Now if you look at what you've been given, right, we've been given this here, right, the 50 millimeters, right, which we get from this perspective. If you look at the flywheel from this perspective, so from the front view, right, this here, right, would be the A, right, and then if you come from the side view, this is what you would get, the 40 millimeters, which is the B, right? So essentially to get the area here, because we have this entire distance and we have this one as well, right? And we have this entire distance and we have this entire distance, but we're not necessarily looking for this entire distance or that entire distance. We're looking for half of those distances, right? So this would actually be half into A over 2 times B over 2, right? Okay, not B, not A, this would actually be, so this whole distance, right, this whole distance, what should I call it? Okay, maybe let me call this, for this to make sense, what is this? So let us call this, okay, let us call it A for now and call this B, right? My point is what we are looking for is half of this distance and half of that distance, right? And then this, of course, would then be pi over 4 into A times B, right? That is where essentially that is where this formula actually comes from, right? And now we substitute, right? So this here is 7200 times pi over 4 into the 50 millimeters, which is 0.05, times the 40 millimeters, which is 0.04, right? Times the length of the spoke, right? Now, as far as the length of the spoke, right? There's the spoke here. So this is the length of the spoke we are referring to. So from here to there, right? Now, the distance we have is from here to there, which is the 250 millimeters. But we are looking for the distance from here to there. So the distance we are looking for is this one, right? Now, how do you go about getting the distance? You simply say the 250 minus the 90, right? So 250 minus the 90 gives us 160, right? It gives us 160. So this length is 160 millimeters, which is 0.16, times the number of spokes. We have 6 number of spokes, right? Now, if you punch this in your calculators, we are going to get 0.031 kilo, not this. So if you punch this in calculators, we are going to get 10.857 kilograms, right? That will be the mass of the spokes, right? And then now we calculate the radius of gyration squared, right, of the spokes. Now this one, right, this one you use this formula, right? So it would be the length of one spoke, right, squared divided by 12, right, plus open brackets length of spoke divided by 2 plus the radius of the boss, and you square all of this, right? To make this simple, right, I've come up with this formula, right? So we use this formula, right, for the spoke in particular to calculate its radius of gyration squared, right? Length of the spoke, we've already established that it's 160 millimeters. So this would be 0.16, right, squared divided by 12, plus length of the spoke, which is 0.16, that divided by 2, plus the radius of the boss. Remember, radius of the boss, right, is this one here. So from here to there, which is that 90 millimeters, right? So this would be plus 0.09, all of this squared. Now punching this in your calculators, we are going to get 0.031 kilogram meter squared, right? So we have the mass and we have the radius of gyration squared. Right, so now we'll be able to calculate the moment of inertia for the spoke, which will be, of course, m times k squared. Right, so now you substitute the mass is 10.857 times radius of gyration squared, which is 0.031. Right, now we punch that in your calculators. and we get 0.337 kilogram meter squared. Let me just make sure that's the case here. So we have 10,857 times 0.031. Yes, 337. Right. So we've calculated everything regarding the spoke. Right. Now we move on to the shaft. Right. So we calculate the mass of the shaft. So SH stands for shaft. Right. Now we calculate the mass of the shaft. Right. Remember to calculate the mass, since we have the density, right, it will be rho times the area of the shaft times the length of the shaft. Right. Now we have the diameter of the shaft and we have its length. Right. The shaft is this one. Right. So the shaft is obviously circular. Right. So we simply use pi r squared for our area. Right. So this would be rho times the area, right, the area of which will be the pi r squared, right, radius of the shaft, so pi times radius of the shaft squared times the shaft length, right. So this is equal to the 7200 times pi into radius of the shaft. Remember, the shaft is 100 millimeters in diameter, right? So all you do is divide that by 2, so you have 0.05, right, squared times the length, which is 1 meter. Now, punching this in your calculators, we are going to get the mass of the shaft as being 56,549 kilograms, right? Right. So now we calculate the radius of gyration squared. So the radius of gyration squared, right, for the shaft, right, would simply be half times the radius of the shaft squared, right. This is half into radius, which is 0.05 all squared, right. Now if you punch this in your calculators, we are going to get 1.25 times 10 to the negative 3 meters squared, right. We have the mass, we have the radius of gyration. Now we can get I, right, of the shaft. Of course, this is mk squared, right. The mass we got is the 56,549, right, times radius of gyration squared, which is 1.25 times 10 to the negative 3 meters squared. Now the product of this gives us 0.071 kilogram meter squared, right. Now we are done with that part. So now we move on to the rim, right, which will essentially be the last part here, right. We've looked at the boss, the shaft, the spoke. Now we look at the rim, right. So now we look at the rim, right. So we first calculate the mass of the rim. So R stands for rim, right, and this will be rho times the area times the length, right. Now as far as the area of the rim, right, the area of the rim, right, we essentially look at the outside radius of the rim, right, and we subtract that with the inside radius of the rim, right, to get the area, right. And then as far as the length of the rim, right, the length of the rim we would get from this view, right, we would get from this view, right? So essentially it would be the width, right? Essentially it would be the width, which is this one, right? If you look at the flywheel from this perspective, right? So coming from that direction, side view, right? You would then get this here, which is the length, which essentially, as far as the rim, would be the width of the rim, right? So here you have, this would be the outside radius squared, right, minus the inside radius squared, right? I forgot the pi. So this would be pi, right, times the length, which, as we've established, is actually the width of the rim, right? So this here, 7200 times pi into the outside radius, right? The outside radius, which would be the radius from here to there, right? Now the distance from here to there is the 100 plus the 250, right? So which is 350 millimeters. So this here is 350 millimeters, which is 0.35 squared, minus the inside radius, right? The inside radius, right? The inside radius, which would then be from here to there, right? So from here to there is the outside radius, and then the inside is from here, so this here, right? So the inside is from here to there, which is the 250, right? So this is 0.25 squared, right, times the width, which is 100 millimeters, so that is 0.1, right? Now if you punch this in your calculators, we are going to get 135, right, 717 kilograms, right? We've calculated the mass. Now we calculate the radius of gyration squared of the rim, right? Right, so this will simply be half into, right, you simply take this as it is, with the sign here will be different, right? So you take this as it is, but now instead of minus, it's going to be plus, right? So this will be RO squared plus the inside radius squared, right? This is 0.35 squared plus 0.25 squared, right? And then this will be equal to 0.093 meters squared, right? So we've calculated the mass and the radius of gyration squared, right? So now we can get I of the rim. I is m times k squared. The mass is 135,717, right, times k squared being 0.09, right? Punching this in our calculators, we are going to get 12,622 kilogram meter squared, right? Now the question was calculate the moment of inertia of the wheel and the shaft assembly around the axis of rotation, right? So we're looking for the total, right? Right, IT, right? So IT, since we've calculated the moment of inertia for each part, now all we do is you just add them, right? So this would be I of the boss plus I of the spoke plus I of the shaft plus I of the rim. It's 4 parts, right? Yes. Right, so now you just add these, right? In adding these, for this one we got 0.101, right, plus the 0,337 plus the 0,071 plus the 12,622, right? And here I got 13,131 kilogram meter squared. Right, that is how we would go about such a question. Right. So now we look at 3.2. Right, 3.2. What are we looking for? The radius of gyration of the whole system. Right, pretty straightforward. Not radius of gyration. Yes, radius of gyration. Right, of the whole system. So they are now looking for K. Right. Now we know, right, I is equal to mk squared. Right. So IT would be equal to the total mass, right, of the whole system, right, of the whole flywheel. So the mass of all the parts put together, right, times the total or the radius of gyration, right, of the whole system, which is what they're looking for, right? This is what they're looking for, right? This we've already calculated, so it means we have to calculate this, so we'll be able to calculate that, right? So we calculate MT by putting together the masses of all the parts. So this will be the mass of the boss plus the mass of the spoke, or the mass of the spokes, plus the mass of the shaft plus the mass of the rim. Right, so this will be equal to, we got 19 here, plus the 10,857 plus the 56,549 plus the 135,717, right? And here we get, 222,123 kilograms, right? So if you look at this formula here, this is what we're looking for. So just K, we have this, now we have that, so we can get K, right? To get K, making K the subject of this formula, right? This would be total K is equal to the square root, right? The square root of I total divided by M total, right? So this will be equal to so I total is 13,131. So this is 13,131. Right, divided by the mass total. Mass total is 222,123. Right. Right. Now if you punch this in our calculators, you're going to get 243,138. Right, and this will be, now this I've expressed in millimeters, right? You don't necessarily have to express this in millimeters, but for accuracy purposes I like expressing my quantities that will be in meters or in millimeters in millimeters, right? And that is how you would approach such a problem on flywheels, right? Like I said, most of the problems, right, so other problems outside of this one, right, where you've been given the diagram of, or where you make use of the diagram of the flywheel in order to be able to do your calculations, right? Most problems outside of this, you just require extensive knowledge on angular motion, of which if you do, you should come right with flywheels. Right, so flywheels are pretty straightforward. Right, if again you have extensive knowledge regarding angular motion. Right, hopefully you found this video helpful. Right, if you did, please give it a thumbs up. Right, like, subscribe, share with your fellow students. Right, all the best. Yeah, cheers.